Okay, thank you very much for having me here. It's my great pleasure to give a talk. I'm going to talk about the universal microscopic mechanism of hybrid population transition. I belongs to Korean Institute of Energy Technology. This university is very brand new, so opened this March. So this institute, the university is focused on the energy science and the engineering. The outline of my talk, so it consists of this list. So my aiming is the uncovering the universal mechanism of a hybrid population transition in cluster merging process at a microscopic level. To explain the hybrid population transition, I would like to talk about some background about the hybrid phase transition and the hybrid phase transition equilibrium system and non-equilibrium system, and synchronization and epidemic transition. And I moved to the hybrid population transition problem, and it occurs in a cluster pruning process and cluster merging process. So I eventually focus on this part. Let me get start hybrid phase transition in equilibrium system. This is the behavior of the order parameter and the susceptibility for second order continuous transition. The order parameter increase continuously like this, and the susceptibility diverges at the transition point. And in the first order, for the first order transition, order parameter jump, and but the susceptibility does not diverge, the finite value. In hybrid phase transition, order parameter jump and next increase continuously. This part exhibit some critical behavior. So the susceptibility from this side does not diverge, but it diverges in this side. For Landau theory perspective, the second order transition free energy exhibits some parabolic behavior at above the transition point, and there's a double well potential shape in for lower temperature than the transition point. And free energy can be written this way, and for the second order transition, T star means that TC, and W becomes 0. But for the first order transition, the T star is not TC. And W is not 0. It can be positive. It's a minus sign here. So it exhibits these types of behavior. So let me focus on some future property of the second derivative. For the second order transition, second derivative of the first free energy becomes 0 at TC, but the second derivative for the first order transition does not exhibit the 0. The second derivative is positive here. For the hybrid phase transition case, the free energy is here 0, but the second derivative as well 0 as well, and at this transition point, the second derivative is here 0, and this is also the minimum, so that after TC, the transition order parameter has a local minimum here. If you look at the phase diagram, then the second order transition line meets on the first order transition curve. Actually, when for the tri-critical point, if second order transition line meet the first order transition line at the critical point. So to occur the hybrid phase transition, there exists a critical endpoint at which the second order transition, first order transition meet on the first order transition line. As an example of the spin model that exhibits hybrid phase transition is the Ashkin-Taylor model on scale-free network. Ashkin-Taylor model was introduced a long time ago. The model was introduced to consider the four-spin interaction, Hamiltonian interaction. So, but recently we applied this Ashkin-Taylor model on the complex scale-free network, where the one types of spin corresponding to the there exists two different issues. So one spin represents one issue, and the other one is another issue. And this corresponds to the one layer of the scale-free network, and this is the other layer of the scale-free network. And so for this Hamiltonian on scale-free network, so we found that it's a very complicated phase diagram like this. There exist three phases, paraphase and the Baxter phase and the sigma S phase. There is a first order transition line, and this is a second order transition line. So there exists some critical endpoint. At the critical endpoint, we found that the order parameter exhibit a jump here and the continuously increase as temperature reduce. So let me move to the non-equilibrium case systems. As an example is a synchronization problem described by the Kuramoto model. A Kuramoto model is described by this one, where we use some flat distribution of the intrinsic frequency. So omega is between minus gamma to gamma. The G omega value is 1/2 gamma. It's a flat distribution. Otherwise, it's 0. Then we can, for this, actually this model was studied by the Pacho 2004. Recently, we considered the ad hoc potential to understand some this kind of hybrid transitions in terms of the ad hoc potential. So we construct a self-consistent equation this way. This is well known, and we define the some kind of ad hoc force, which it is defined FR. FR is this one and minus R. Then it's equals 0 at the minimum of the potential at star. Ad hoc potential defined from the this ad hoc force. So we calculate using this formula the UR. And then UR, as expected, this is 0 up to the transition point and increase continuously, exhibit hybrid transition like this. Another example is the simplicial SIS model, epidemic model in scale-free uniform hypergraph. Here, eta is a control parameter, is the infection rate divided by the recovering rate. And the rho is the fraction of infected node. So when the lambda is above some characteristic lambda c, then the epidemic transition exhibit a hybrid transition like this. This is consistent of the analytic result. Let me move the hybrid population transition. Historically, the population transition is well known as the robust continuous transition. But in 2009, some explosive population transition model was introduced. And first, at the beginning, it argued that the discontinuous transition, but later it turns out to be continuous transition. But by this paper, if this order parameter, the population transition model include some global suppression rule, then it can show the discontinuous population transition. Additionally, we include criticality to this global suppression rule. Then we found a hybrid population transition model. Hybrid population transitions can be classified into two types. One is the branching process. One is the pruning process. The other one is the cluster merging process. So let me we focus on these types problem, and these types of problem was well studied before, and I'm going to recall the previous result. This is the original population model and exhibit the second order transition. And the Erush-Rayni model is the good example for mean field result. And it exhibits the second order transition. So in this nowadays we apply the dynamic rule to generate the Erush-Rayni graph. So at each time steps we select two nodes and unconnected, then add a link one by one. So this is kind of dynamic problem. And the criticality of this Erush-Rayni model can be described by the cluster size distribution. The cluster size distribution exhibits this Paolo behavior with some exponential cutoff. And this cutoff characteristic size also exhibit the criticality with the exponent sigma and the tau here. So exponent tau and the sigma are two important critical exponents to describe the Erush-Rayni model. However, if we measure directly the giant component size divided by system size, then this exhibit Paolo behavior like this, and the order parameter can take that way instead of the first moment of the cluster size distribution. However, this definition and this definition reduce the same one for the second order transition. So for the second moment of the cluster size distribution, it represents the mean cluster size of the population, but this also exhibits the Paolo behavior like with the exponent gamma. And if we define the order parameter fluctuation as a susceptibility, it shows the same behavior like this. So for the second order transition, these two representations reduce the same. So we are not confused. But for the hybrid phase transition, that these two represent can be different. Interestingly, this tau exponent value and the sigma has a relationship in Erush-Rayni model, tau plus sigma equal 3. So for this critical the pruning process, okay, so let me briefly introduce the result for the hybrid population transition. The order parameter can be described by this way, and the cluster size distribution for the finite clusters can be described by this way, and there exists some giant clusters of size order n. So as I told you, this represent two representations are not always same. So we introduce two types of exponent, critical exponent. One type is associated with a critical cluster size distribution. The other one is associated with a order parameter. And gamma S was obtained by this formula. It's not same as the gamma M. Gamma M is obtained from the fluctuations of the order parameter. However, these two types of exponent value are not totally independent, but related to each other using this formula. The gamma S is equal to 1 minus beta. Across the pruning process goes this way. So for this case, this jump discontinuity does not affect to the critical behavior of the order parameter here, but for the cross merging process, the jump behavior discontinuity can affect the critical behavior of the order parameter here. Let me first consider the cluster pruning process. A typical model of the cloning population transition is K-core population. K-core, for example, is a network here. So if you consider the K-core 3 core, then the network of each node of the network has to have a degree, the number of connection at least 3. So for this case, if we remove a node with a degree less than 3, then for example this one, then this node has had some degree 3, but if we remove this one, the degree of this node becomes 2. So this node is not does not belong to K3 core. So this this node is already also removed by this. So the central 4 node only the K3 core. For this problem, because here as we remove this node, the blue node and the yellow node disappear, because it does not belong to K3 core. So that number of the removed node is regarded as the avalanche size. So as we as we go this way, their node are removed and the avalanche dynamics occurs. So we can consider the avalanche size distribution. And this one is the average avalanche size. Then the order parameter plus the avalanche size summation accumulated the avalanche size has to be 1, like this. So using this relationship, we can derive this one. And if we consider the singular behavior, then from the left-hand side, we can obtain the beta m minus 1. On the right-hand side is minus gamma a. So this relationship, this relationship can be obtained. Particularly, we can, for this kind of a problem, so we can derive the beta m analytically. So beta m becomes 1/2, and the gamma a is 1/2. This one can be obtained analytically. I'd like to notice that for the cascading avalanche dynamics occurs in tree-like structure. So that, for example, if this node has 3, if we remove this one, then the degree of this node becomes 2, and degree of this node becomes 3, like this, and go on. Then later this one becomes 4 and 2, 4. so that the tree-like behavior. So if you measure the branching, the mean branching ratio, then we can find that the mean branching ratio becomes 1, so that is a critical branching tree. So we can find the critical branching by the avalanche dynamics of the K-quad population. So that the avalanche size distribution exhibit the power law, and the susceptibility is the avalanche mean avalanche size. It becomes also the exhibit is a power law, or this corresponds to the gamma A, so that the avalanche size critical exponent of the gamma A, gamma A is determined by the critical behavior of the avalanche dynamics. So the pruning process, the criticality is not affected by the discontinuity. A critical branching process is a main microscopic mechanism of this hybrid transition. And the criticality of the hybrid population transition is determined the critical behavior of the avalanche size distribution. And the two set of critical exponents is required to describe the criticality, and they are linked like this. This one is obtained from the obtained pruning process, and not only K-core but also the many cascading dynamics association population has the same universal feature. Let me move to the this issue, population of the by the cluster merging process. As time is the number of link divided by the n. So if we add link one by one, then the dynamics goes this way, like this. When a T core this area, then the cluster size distribution exponentially decay. And at this point, this one at this point, cluster size distribution exhibit the power law in small s. There is a bump here, and as the order parameter increase this way, jump like this, then this bump size reduced, and at this point, cluster size distribution exhibit the power law, and after that, the critical cluster size distribution decay exponential power law way and the exponential way after the characteristic size. If you look at the order parameter from the one single configuration, if you look at the order parameter as a function of time, then this square means that the cluster merging occurs. For the giant component, largest cluster, then this in this region, this means that in this subcritical regime, the order parameter increase very slowly, like this. But during this way, this is interval here, order parameter increase like this stairway case, the infinite level staircase like this. And we have some three regimes, this one and this one and this one. And this narrow region, so before there is a TG. At TG is not this at TG. Sorry, at TG, there still remain a little bit bump, and after TG, the suppression effect is disappear, and the dynamics is governed by purely Erdos-Rayleigh types dynamics. So that at TC, we can find that the cluster size distribution power law behavior. Let me explain you a little bit detail for this mechanism. And suppose the growth of the giant cluster is suppressed. So I will explain you later. then order parameter exhibit bump, right? And at this regime, the order parameter exhibit the Debye staircase, and we classified into three regimes: this region, then this region, and in this region's bump formation, and in this region, a bump relaxation occurs, and so giant cluster grow, and in this narrow regime, and then the suppression effects disappear, and the error distribution dynamics occurs. And if we this is the numerical simulation in finite system. So if we measure the interval between this way and this, between this one and this point, and the interval between TA and TC, and if we measure this one for different system size, then this one can be reduced to zero. So that in thermodynamic limit, we regard the population transition is discontinuous up to TC. Okay, and so this instead means that we introduce inter-event time. Intermittent time here means that the interval between successive merge that occur node are involved, or node is involved the time interval between the two successive merging, then the interval becomes exhibit a power law behavior in subcritical regime, and also the power law behavior in the transition to period. So the power of this exponent value, this power law behavior, and this was are different. This power law behavior determine the criticality beyond the transition point here. So this for cluster merging process, we need we need two types of critical exponent value associated with the cluster size distribution and the order parameter respectively. And this unified some scaling relation is also hold for this problem. So to explain you the detail of the mechanism, we introduce two models. First is called the restricted random network model. The clusters are classified into two partitions. So in this partition, small size clusters are included, and this one, this partition include the large clusters. So the number of nodes belongs to this partition is G times N. And we select two nodes randomly. One is randomly selected from entire system, and the other one select only the this set, so that two node cannot be selected from this large set. So this rule effectively suppress the growth of the large cluster. And originally, this rule is very rigorous, so that if a cluster is on the border, then the part of the one belongs to R set, the other one belongs to RC set. However, for us, physicists, is very simplified, and then this one regarded as belonging to R set. All node belongs to this cluster. Actually, this slightly modified rule enable to generate a hybrid population transition. Order parameter as a function of time the L over N, L is the number of link added, then it shows the hybrid transition like that. And the order parameter described by this way. The exponent beta, it depends on the G. G is defined here. The Gn number of nodes belongs to this cluster. So when G is large, that means that the suppression strength is so good, so large. Sorry. When G is large, then suppression strength is small. So when G equal 1, then means that total node belongs to one set, so that it reduced to the Erdos-Renyi model. So when G is small, that means that suppression rule is very strong. So most clusters are restricted. Then as G is smaller, the cluster size order parameter jump like this and continuously increase this way. When G equal 1, then it reduces to the Erdos-Renyi case. As I told you, then when we regard this one belongs to this R set. So when the largest cluster fill this partition, then because two partitions cannot be distinguished, so that the model reduced to the Erdos-Renyi model. We consider the inter-event time. Inter-event time means that a node or a cluster which belongs to tracing the node, and when the node is connected to other node, then the cluster size becomes bigger. Then if this cluster size is bigger than the criterion, then it moves to this one. And then a small cluster here has to move this way. And then we can count number of time, the time during which this one node belongs to one set. So, for example, this node when this cluster moved here, a node belongs to this one get the stopwatch t equals 0, and after going this way and up to return to the partition B, then we can data time is regarded as inter-event time. Then a node is in the set A, this interval, and set B, this interval, and set A, this one enters. This interval, this inter-event time exhibit the power law, this one and this one. It has a different exponent alpha prime. This alpha is here. So we can analytically we derive that alpha is related to cluster size distribution exponent, tau, and the sigma. So for this regime, the alpha is 4 minus tau minus sigma, so it's not prime, so sigma. But as I told you, the tau plus sigma is 3 for the Erdos-Renyi model, so the alpha equal becomes 1. So that if this slope is slope 1. In this regime, the alpha prime is because sigma becomes 0, the alpha prime becomes 4 minus tau, so that tau alpha prime depend on alpha determine the tau. So or tau is determined the alpha prime. This. So using finite size scaling analysis, we obtained that 2 beta m plus gamma m is nu m bar, and 2 beta s plus gamma s is a new s bar. Sorry. And so two exponent relation has a scaling relation itself. and for order parameter and for cluster size distribution. But this alpha s plus beta m equal 1. So numerically, we found that 1 plus minus 0.1 when g equal 0.5. So this is a very useful factor, and this result can unify the some critical analytical behaviors in subcritical regime and the pruning process and the merging process. As a second model for the hybrid population transition plus the merging process is BFW model. So the model was introduced by mathematicians, so it's a little bit confusing and complex to in a short time, but there exist some parameters. L is the number of link added in practically, but U is the number of trials. So if governor does not allow, then to suppress the growth of the largest cluster, the governor can allow or not allow, disallow. So L is the success. This L over U is the success rate. K is the upper bound of cluster size. If the K, the largest cluster, is larger than K, then a little bit governor does not allow for link addition. However, if this trial is so small, then means that many people want to growing the largest cluster, but not allowed. But then governor becomes generous, so that it open the door to largest cluster can increase. This kind of mechanism is kind of can be applied to some financial system, and so that by this mechanism, so that the boom and boost behavior occurs. Original model G depend on there's a parameter G, and G depend on K. So original model used this one, but this original model does not give us the hybrid population transition, just a continuous transition, and discontinuous transition. Sorry. But if we use GK as a constant, then the L over U is a success rate equal 0. If G equal 0.5, then the governor becomes generous. This one touch the G value, then governors allowed to attach the bigger size cluster to allow the making the bigger size cluster, and the bigger size cluster increase a little bit and down and like this. So this K corresponds to the large giant cluster size. So jump and jump and jump like this. So this model exhibits the hybrid population transition. And the giant cluster size distribution exhibit a bump below TC, but at TC it exhibits a power law behavior like this, and in subcritical regime it exhibits the power law and the decay exponentially. The exponent tau, it depends on some control parameter G. Means that tau is depending on the suppression strength, so that depending on the suppression strength, the criticality, critical exponent exhibit continuous varying behavior. Similar to the restricted ER model, BFW model exhibits 3 characteristic regimes. and in this narrow regime occurs is in self-organized way, like this. And we consider this restrictive percolation transition in 2 dimensions, and we found that the fractal dimension cannot be described by this the formula used in the original percolation because the giant component. And we also applied the restrict rule to synchronization problem. It also shows the hybrid transition behavior. So we studied these problems alone. So the part of them are listed here. And this is the conclusion for cluster pruning process case, and the cluster merging case also, this one. And this one pictures with my colleagues here. Thank you very much.
Thank you very much for the talk. We have a few minutes for questions. Yeah.
More like a curiosity. I mean, I never heard about this hybrid kind of transitions. So, do you know a quantum system where it can be found?
Quantum systems, we studied some quantum contact process in scale-free networks. At that problem, we found the hybrid transition.
Okay,
The
thanks.
reason is that because in Landau picture, usually in Euclidean space, the free energies expand in terms of the order parameter. So the power is an integer value. But on the scale-free network, the power can be a real number, so that it can make a hybrid phase transition.
Thanks.
Any other questions? Thank you. In that case, let's thank the speaker
Thank you very
again.
much. Yeah.